Welcome back. So, in the last lecture we have started module 2 and we were discussing about the basics of shear strength. We have discussed about Coulomb's model, which is applicable for granular materials like soil. Then we discussed about integrating Mohr circle with Coulomb's model, and that is how we got Mohr Coulomb failure envelope. And we discussed about some basic facts about Mohr Coulomb failure envelope and how important it is for materials like soils in defining the failure criterion. Now, it is a continuation of that particular lecture. We have seen that we have represented the stress in terms of shear stress and normal stress. Now, there are various other ways of representing stresses for different failure criterion. So, today's this particular lecture we will see what are the different representations of stresses for defining the failure of a material. So, the first one is about different stress representation. The first one is familiar to us, which is tau versus sigma dash, where sigma dash is the effective normal stress. Now, you need to note a specific point here. I have started introducing dash or prime. Now, this is very important because now we have started the actual discussion of strength, and we know by effective stress principle strength is completely governed by the effective stress. So, we have tau versus sigma dash, and this is a typical Coulomb failure line or Mohr Coulomb failure line. We need not discuss about this anymore, we have already seen this. Another way of stress representation is major principal stress versus minor principal stress, and we will get a line here and that is the failure line within which the soil remains. The possible stress states of the soil remains. We also have discussed and we have also seen sigma 1 dash by sigma 3 dash is the stress obliquity. Sigma 1 dash by sigma 3 dash is stress obliquity, and we have also discussed about maximum stress obliquity in the last lecture. So, this is another way of representing the stress, or as a modification of this one, we can also represent in terms of a more general term where it is axial stress versus radial stress, and all normal stresses need to carry this dash or prime indicating that it is effective. So, sigma A dash is axial stress and sigma R dash is radial stress. So, you can also plot between sigma A dash versus sigma R dash, and again there is a failure line and the slope of the failure line is represented by Kf. So, in all these representations the slope of the failure line is Kf. So, these are some different ways of stress representation. Now, to be very specific in terms of failure criterion, we also have some other representations, which is Q P dash plot, or it is known as Cambridge plot, possibly due to the contribution towards this from the research group at Cambridge. So, we will see for specifically for triaxial condition. In general, we have already seen what is Q, what is P dash. What is Q? Q is deviator stress and P dash is mean stress. For 3-dimensional state, we have discussed this in general in our previous lectures. Now, here we will specifically confine our discussion to triaxial condition because that is going to be a very prominent condition for soils. All our determinations in the lab confines to mostly triaxial condition, or in other cases it will be plane strain condition. Whatever be, in today's representation we will confine to triaxial condition, and Q and P dash for triaxial condition we have already evolved in the previous lecture. Accordingly, we know P dash, that is the mean stress, is sigma A dash plus 2 sigma R dash by 3, which is equal to, or you can write in terms of principal stresses as sigma 1 dash plus 2 sigma 3 dash by 3. Now, let me make it a point clear here. It is always better to write in general terms, and when I say general terms, I mean in terms of axial and radial stresses. Why? Because whether sigma A dash, that is axial stress, equal to major principal stress will depend upon certain condition. We will see that in the subsequent slides. So, I would always suggest that we write P dash and Q in terms of axial and radial. For the time being, let us not worry about the major minor principal stress. So, triaxial condition, what is the triaxial condition? We have already seen, I will not discuss that. Sigma A dash plus 2 sigma R dash by 3, because all round stresses. So, sigma 2 dash equal to sigma 3 dash. So, in the all round stress it is same. So, 2 sigma R dash by 3, Q is equal to sigma A dash minus sigma R dash, or it is sigma 1 dash minus sigma 3 dash. This may change depending upon conditions. So, that is why we will confine to axial and radial. So, here in compression you will see that sigma A dash or the axial stress is equal to sigma 1 dash and sigma R dash is equal to sigma 3 dash. This is a typical triaxial condition that we deal with in the lab. Now, if you swap it, that is sigma A dash is equal to sigma 3 dash, sigma R dash is equal to sigma 1 dash, it becomes a typical case of extension. Why? It gives more like a squeezing effect. So, sigma 1 dash is more, so it has a tendency to extend. So, that is a typical case of extension, and this is a typical case of compression. So, if you want to specifically define in terms of compression and extension, then it is always better that we define the stresses in terms of axial and radial. That is the point I want to make. So, we will confine to that. Now, let us see the slope of the failure line in Q P dash plot. So, what is the slope of tau versus sigma plot? It is nothing but phi dash. So, that is the slope. Similarly, we want to find out what is the slope of failure of Q P dash plot. So, this is Q P dash plot, and I have drawn two lines. These are failure lines, and one line corresponds to the case of compression, the other line corresponds to the case of extension. So, depending upon whether it is compression or extension, we need to take appropriate stresses, and that we have seen in the previous slide. So, Kf is nothing but Q by P dash. Now, we are taking the case of compression. So, this means that sigma A dash is equal to sigma 1 dash, sigma R dash is equal to sigma 3 dash. Substitute for Q and P dash, that will give sigma A dash minus sigma R dash divided by sigma A dash plus 2 sigma R dash by 3, always represent in terms of axial and radial. So, this is what it is. Substitute for sigma A and sigma R, that will give you this expression. Rearranging, you can take sigma 3 dash outside. So, it will become sigma 1 dash by sigma 3 dash minus 1, sigma 1 dash by sigma 3 dash plus 2. This divide by 3 goes into the numerator. Now, we have sigma 1 dash is equal to sigma 3 dash tan square 45 plus phi dash by 2. This is as per the Mohr Coulomb failure envelope. Now, this is not going to change, this remains same. So, we have what is the ratio. Now, this is for C dash is equal to 0. We are not considering cohesion for the time being. So, we will consider the Mohr Coulomb failure envelope, that will give sigma 1 dash by sigma 3 dash tan square 45 plus phi by 2 is equal to 1 plus sin phi dash by 1 minus sin phi dash. You substitute this in this particular expression of Q by P dash, that will give you 3 into 2 sin phi dash by 3 minus sin phi dash. So, the failure envelope, the slope of the failure envelope will be Q by P dash is equal to 6 sin phi dash by 3 minus sin phi dash. Remember, This is for the case of compression. Now, the same can be obtained for extension as well, that we will see later, maybe as a part of assignment. For the time being, this is only for compression. So, what we have done for a specific representation of stresses in terms of Q and P dash, we have defined the failure line. Remember, this is going to be useful throughout this course. Why? We need this in stress path, we also need this in critical state module as well. So, please pay more attention to this. Now, another representation of stress is TS dash plot, or it is called MIT plot, or it is known as maximum shear stress plot. What is maximum shear stress? When you draw a Mohr circle, we know that there is a maximum point that we obtain, and we have seen that this maximum point is not the stress which causes failure, but a critical combination causes failure. So, here we will specifically talk about the maximum shear stress point. If you draw a Mohr circle, I am talking about this particular point. This is the maximum shear stress point, and if you discuss it in terms of sigma A dash or sigma R dash, this point will be sigma A dash, this is S. So, sigma A dash plus sigma R dash by 2, and T, which is this distance, is T, that will be sigma A dash minus sigma R dash by 2. So, again we have represented in terms of axial and radial stress. So, here it is the typical representation of T versus S dash. So, T is sigma A dash minus sigma R dash by 2, and S dash is sigma A dash plus sigma R dash by 2. These two represents the maximum shear stress point. So, here we are representing it in this form, and there is compression line and extension line. We need to find out what is the slope of the failure line in S T dash plot. So, S dash T, remember S dash we have put prime, T we have not, because this is more like a shear stress. So, U cancels off. So, you can T is equal to T dash. So, S dash T is the locus of maximum shear stress point. We have already discussed that. Now, let us consider T S dash plot. This is the Mohr circle. We have represented Mohr-Coulomb failure line. We have represented. So, that is the point C at which the tangent goes. We also have this particular point through which you can draw a line. So, if the Mohr-Coulomb failure envelope is given by red line, from the same point we can also draw a line which passes through the maximum shear stress point, that is point B. So, the inclination of Mohr-Coulomb failure line is phi dash, and let us say the inclination of the line passing through maximum shear stress point is alpha. So, this inclination is alpha. What is this point? That represents S dash and T point. Now, this particular intercept is given by A dash, the inclination, that is the line passing through maximum shear stress point makes an intercept of A dash, and we know the intercept of Mohr-Coulomb failure line is C dash. I have not marked it because we already know it. If I mark it, it becomes more cumbersome. So, I am not marking it. So, this is how it is. We want to find out what is the inclination of this particular line, because we are talking about the maximum shear stress point. Accordingly, we can write a modified failure envelope which is different from Mohr-Coulomb failure envelope, that is T. For Mohr-Coulomb it is tau. So, here it is T is equal to A dash plus S dash tan alpha, alpha is the inclination. So, it is more or less very identical to Mohr-Coulomb failure envelope, only thing is the parameters changed. So, what is tan alpha? That is the slope. So, we want what is tan alpha, this one. So, that tan alpha can be written as AB by AD. Now, that is also equal to this smaller triangle, that is A dash by DO. So, this triangle and this triangle is what we have considered. So, tan alpha is the slope what is needed for us. Now, sin phi dash, if you consider triangle DCA, that is triangle DCA, AC by DA is sin phi dash. So, that is what is written here. Now, we also know AB and AC are radius. So, AB is equal to AC, that means this expression and this expression are same. So, AC is equal to AB, hence we can write tan alpha, which is the required inclination of the failure line of TS dash plot, is equal to sin phi dash, and phi dash we know it comes from the Mohr-Coulomb failure envelope. Now, we also know tan phi dash is equal to C dash by DO, that is tan phi dash, considering the red line, the intercept is C dash divided by DO. If I write tan alpha by tan phi dash, where tan alpha is equal to A dash by DO, we can write A dash by C dash. So, tan alpha by tan phi dash is equal to A dash by C dash, from which we can write, how will we get this? So, tan phi dash, we have already seen tan phi dash is equal to sin phi dash, we have already proved. Substituting that here in this expression, tan alpha is equal to sin phi dash, here it will be sin phi dash, that will cancel off and cos phi dash goes up. So, it will be C dash is equal to A dash by cos phi dash. So, slope of the failure line of TS dash plot. So, this plot is tan alpha and that is equal to sin phi dash. So, what we have done? We have defined the Kf or slope of the failure line Kf of TS dash plot. Remember, when you do a triaxial testing, those who have not gone through this during their undergraduate, I am just adding this detail here. When you do the triaxial testing, what you will get is, you will get the deviator stress at failure, that is sigma 1 dash minus sigma 3 dash at failure, and you know the confining stress is sigma 3 dash, sigma 3 dash. So, you know what is sigma 1 dash and sigma 3 dash. Sigma 1 dash, sigma 3 dash known. Now, what will you do? You need to plot the Mohr circle and get the shear strength parameters C dash and phi dash as applicable. Now, if you know this S dash T plot, you need not plot the Mohr circle. From the known values of sigma 1 dash and sigma 3 dash, one can always find out different points, that is S1 dash T1, S2 dash T2, S3 dash T3, and plot this blue line. We will get maybe 3 points, corresponding to that we will get 3 points here in TS dash plot. One can always plot this blue line. Once the blue line is plotted, we can get A dash and alpha. And once you know A dash and alpha, we also have the expression tan alpha is equal to sin phi dash. So, alpha is known, tan alpha is known, we can always determine phi dash. Similarly, we have this expression C dash is equal to A dash upon cos phi dash, phi dash is known, A dash is known, C dash can be determined. So, the Mohr-Coulomb failure envelope parameters can be obtained without plotting the Mohr circle, once you know the concept of TS dash plot. Okay? So, that is all about that. So, we will summarize this first lecture, that is granular materials like soils fails in shear. We have already told this, we need to keep this in mind. Coulomb friction model is the simplest model that represents shear strength of soil. But remember, Coulomb's friction model, it depends upon the development of a failure plane within the soil mass. Shear strength parameters C dash and phi dash, these are not fundamental properties of soil. Now, when I say this, there will be some for whom this is difficult to understand. Why it is not a fundamental property? Because it is governed by the condition under which C dash and phi dash has been obtained. You are not likely to get the same value all the time, but having said that, there are cases where, or there is a specific condition where it can become means mostly phi dash can become a fundamental parameter. That we will see in the 4th module in detail. So, for the time being, let us understand that C dash and phi dash are not fundamental properties of soil. It could have been a fundamental property if the void ratio and or pore pressure remained constant with normal stress. Now, this is a difficult proposition to make in soils. Either the void ratio, because in drained condition there will be volume change, and when there is volume change, there is change in void ratio. If it is undrained condition, there is no volume change, only pore water pressure changes. That is why it is written void ratio and or pore pressure. If these would have remained constant with normal stress, then C dash and phi dash could have been a fundamental property. You remember when we discussed in the module 1, we said that the volumetric component and the deviatoric component we decoupled. Even though we said that in continuum framework during that lectures, it is very hard to conceive soil without volume change during shearing, which means to say deviatory component also involves change in volume. So, it is very difficult to decouple. So, now subsequent lectures and all our further understanding, volume change component is still there during shearing. We are not actually able to decouple it, even though in the tensorial framework it is decoupled. So, this understanding one should have. So, it should not lead to confusion. It has been said there it is decoupled, why it is not decoupled? It is decoupled in that framework, mathematical framework, but then it is difficult to decouple to understand the behavior of soil, because there will be volume change. Now, if the shearing would have happened at constant volume, probably C dash phi dash components can be a fundamental parameter, which we are not able to achieve. Either the volume change will happen or the pore water pressure would change. So, this prevent the phi dash component to be slightly tricky and not a fundamental parameter. So, this is what I told, it is difficult to maintain this to be constant during loading. So, shear strength parameters are condition specific, and it is very important to mention the condition. Now, later we will see that under certain circumstances it becomes fundamental, rather it will not depend upon the condition. Okay. So, you underline this particular sentence here. For the time being, with our current understanding, we say that it is not a fundamental parameter, but under specific conditions it can be treated as a fundamental parameter. So, Coulomb model integrated with Mohr circle gives the popular Mohr-Coulomb failure criterion for soils. There are different ways of stress representation for failure criterion which has been discussed, and the slope of the failure line, how to determine, that has been discussed for the important ones. And books that may be useful for this particular module is Muniram Budu's book, Halls and Kovacs and Whitlow. These two I have already specified it in the reference, but Whitlow's book is not there. It is R. Whitlow, Basic Soil Mechanics, Longman in 1995. This is also a good book to follow this. I am basically following these books for generating these lectures. So, that is all for now related to basics of shear strength. We have split it into 2 lectures, both confines to basics of shear strength. In the next lecture, we will see the shear strength of granular soil. Now, what we have done is we have splitted it into granular, Granular means basically cohesionless soil and then cohesive soil. So, in the next lecture we will see what is the shear strength of cohesionless soil or granular soil. Okay? Thank you.